Hi everyone, welcome back to my channel Mystic Chemistry Classes. In this video we'll be studying about IR spectroscopy. Infrared spectroscopy. Conditions for a molecule to be IR active. The absorption of IR radiations causes an excitation molecule from a lower to higher vibrational level. We know that each vibrational level is associated with a number of closely spaced rotational levels. Therefore, infrared spectra is considered as vibrational rotational spectra. जब भी एक मॉलिक्यूल एक्साइट होता है आईआर रेडिएशंस की वजह से, तो वो अपनी लोअर एनर्जी से हायर एनर्जी वाइब्रेशनल लेवल पे एक्साइट होता है और हर एक वाइब्रेशनल लेवल में दो वाइब्रेशनल लेवल्स के बीच में बहुत सारे रोटेशनल लेवल्स भी प्रेजेंट होते हैं, जिसकी वजह से इंफ्रारेड स्पेक्ट्रा को वाइब्रेशनल रोटेशनल स्पेक्ट्रा भी कहा जाता है. All the bonds in a molecule are not capable of absorbing infrared energy, but only those bonds which are accompanied by change in dipole moment will absorb in infrared region. सारे molecules infrared region में energy absorb नहीं करते, सिर्फ वही molecules जिनमें dipole moment में change आता है वही सिर्फ infrared region में absorb करते हैं. Such vibrational transitions which are accompanied by change in dipole moment are called infrared active transitions. On the other hand, the vibrational transitions which are not accompanied by change in dipole moment of molecule are not directly observed and hence are infrared inactive transitions. So from here we can draw the conclusion that the important condition for a molecule to be IR active is that the dipole moment, change in dipole moment in the molecule must be present. Example, vibrational transitions of C double bond O, nitrogen and hydrogen, OH, etc. bands are accompanied by change in dipole moment and thus absorb strongly in infrared region, but transitions in carbon-carbon bonds in symmetrical alkenes and alkynes are not accompanied by change in dipole moment and hence do not absorb in infrared region. तो C डबल बॉन्ड O, NH और OH में क्योंकि डाइपोल मोमेंट में चेंज प्रेजेंट होता है तो ये इंफ्रारेड रीजन में एब्जॉर्ब करते हैं, जबकि कार्बन कार्बन बॉन्ड्स जिनमें सिमेट्रिकल एल्कीन्स और एल्काइंस प्रेजेंट है वहाँ पे कोई डाइपोल मोमेंट में चेंज नहीं होता है, इसलिए वो इंफ्रारेड रीजन में एब्जॉर्ब नहीं करते हैं. So on the left hand side, homodiatomic molecule H2 and the heterodiatomic molecule on the right hand side HCl. तो H2 के अंदर कोई भी डाइपोल मोमेंट में चेंज नहीं होता है तो वो IR इनएक्टिव है, और HCl के अंदर क्योंकि डाइपोल मोमेंट में चेंज ऑब्जर्व होता है, H इज़ पॉजिटिव एंड Cl माइनस पे एक डेल्टा नेगेटिव का साइन ऑब्जर्व होता है, इसलिए इट इज़ IR एक्टिव क्योंकि यहाँ पे एक डाइपोल मोमेंट में चेंज ऑब्जर्व होता है इन केस ऑफ हेट्रोडायटोमिक मॉलिक्यूल विच इज़ एब्सेंट इन होमोडायटोमिक मॉलिक्यूल्स लाइक N2, C2, H2. Now we will study about fundamental vibrations, overtones, combination bands, difference bands. ये क्या होते हैं अब हम जानते हैं इनके बारे में. The infrared light is absorbed when the oscillating dipole moment interacts with oscillating electric vector of an infrared beam. For this interaction or absorption to occur, it is important that dipole moment at one extreme of vibration must be different from dipole moment at other extreme in a molecule. Only those vibrations are infrared active which are not centrosymmetric. सिर्फ वही वाइब्रेशंस इंफ्रारेड एक्टिव होते हैं जिनमें सेंटर ऑफ सिमेट्री प्रेजेंट नहीं होती है, जैसे कि हेट्रोडायटॉमिक मॉलिक्यूल्स जैसे कि HCl, उसमें सेंटर ऑफ सिमेट्री प्रेजेंट नहीं होती है। ऐसे मॉलिक्यूल्स इंफ्रारेड एक्टिव होते हैं। The infrared spectrum of a molecule results due to transitions between energy levels. The vibrational energy level of a chemical bond is quantized. और उसकी वैल्यू कैसे निकालते हैं वो अभी हम देखेंगे। क्वांटाइज्ड का मतलब वो एक फिक्स्ड वैल्यू होती है। So E vibrational is given by the formula V plus half h nu, where V is number of vibrational levels, which is 0, 1, 2, 3 and so on. H is Planck's constant and nu is frequency, which is given by the formula 1 upon 2 pi under root k upon mu, where mu is the reduced mass which can be calculated by the formula m1 into m2 upon m1 plus m2. The difference between two energy levels is given by h nu. The vibrations which arise from excitation from ground state to lowest energy excited state are called fundamental vibrations. तो जो वाइब्रेशंस ग्राउंड स्टेट से लोवेस्ट एनर्जी एक्साइटेड स्टेट तक जाती हैं उन्हें कहते हैं फंडामेंटल वाइब्रेशंस। By putting the formula values in the formula, V equal to 1 minus V equal to 0 वाली एनर्जीज को जब माइनस करेंगे तो V equal to 1 पे 1 plus half h nu, 3h nu minus h nu gives you h nu, which is the difference between two energy levels. तब fundamental vibrations कितने types की होती है? Mainly fundamental vibrations two types की होती है, stretching vibration and bending vibration. Stretching vibration is further classified into two types, symmetric stretching and asymmetric stretching, whereas bending vibration is classified into scissoring, rocking, wagging, twisting. So here are the diagrams shown for symmetric stretching, asymmetric stretching, scissoring, wagging, rocking and twisting. Scissoring and rocking are in plane vibrations, whereas wagging and twisting are out of plane vibrations. Overtones result from excitation from ground state to higher energy states, which correspond to integral multiples of frequency of fundamental vibration. सबसे पहले हमने देखा कि फंडामेंटल वाइब्रेशंस कौन सी होती है, जो ग्राउंड स्टेट से लोवेस्ट एनर्जी एक्साइटेड स्टेट तक होती हैं, और ओवरटोन्स कौन सी होती हैं, जो ग्राउंड स्टेट से हायर एनर्जी स्टेट्स में को कॉरस्पॉन्ड करती हैं, जो कि इंटीग्रल मल्टीपल्स होती है फंडामेंटल फ्रीक्वेंसी की. एनी काइंड ऑफ फिजिकल वाइब्रेशन जनरेट्स ओवरटोन्स. If you pluck a string on a cello, the string vibrates with fundamental frequency. However, less intense vibrations are also set up several overtone frequencies. Now, combination bands. When two vibrational frequency mu1 and mu2 in a molecule couple to give rise to a vibration of new frequency within the molecule, and when such a vibration is infrared active, it is called a combination band. V combination is equal to V1 plus V2. Difference bands. The observed frequency in this case results from difference between two interacting bonds. Mu difference is equal to mu1 minus mu2. Further, we will study about another important topic of infrared spectroscopy, which is Fermi resonance. Now, what is Fermi resonance? When a fundamental vibration couples with an overtone or a combination band, the coupled vibration is called Fermi resonance. It is often observed in carbonyl compounds. तो जब भी एक फंडामेंटल वाइब्रेशन किसके साथ कपल कर जाती, ओवरटोन या कॉम्बिनेशन बैंड के साथ, तो उस कपल्ड वाइब्रेशन को कहते हैं फर्मी रेजोनेंस, और ये कार्बोनिल कंपाउंड्स में देखने को मिलती है. This can be explained by saying that a molecule transfers its energy from fundamental to overtone and back again. Quantum mechanically, resonance pushes the two levels apart and mixes their character so that each level becomes partly fundamental and partly overtone in character. Thus, this type of resonance gives rise to a pair of transitions of equal intensity. तो quantum mechanically देखा गया कि पार्टली ये फंडामेंटल हो जाते हैं और पार्टली ओवरटोन हो जाते हैं, और इनकी जो इंटेंसिटी होती है वो इक्वल इंटेंसिटी होती है. दिस फिनोमेना वाज फर्स्ट ऑब्जर्व्ड बाय एनरिको फर्मी इन द केस ऑफ कार्बन डाइऑक्साइड. इसलिए इसका नाम पड़ गया फर्मी रेजोनेंस, क्योंकि इट वाज फर्स्टली ऑब्जर्व्ड बाय एनरिको फर्मी इन कार्बन डाइऑक्साइड. Carbon dioxide is a linear molecule for which 4 fundamental vibrations are expected. So symmetric stretching and asymmetric stretching जब भी आप ड्रॉ करें तो आप एरोज़ का ध्यान रखें कि एरोज़ कैसे ड्रॉ करना है आपको. सब कुछ एरोज़ की डायरेक्शन पे डिपेंड करता है कि आपने सही से बनाया है या नहीं. The symmetric stretching is IR inactive since it produces no change in dipole moment of the molecule. For symmetric stretching, Raman spectrum shows a strong band at 1337 cm inverse. Two bending vibrations are equivalent and absorb at same frequency of 667.3 cm inverse. The overtone of this is 1334.6 centimeter inverse, which is twice of the bending vibration frequency and is close to 1337 centimeter inverse. Thus, Fermi resonance takes place, resulting in shift of first level towards higher frequency. The mutual perturbation of 1937 centimeter inverse, which is the fundamental frequency, and 1334.6 centimeter inverse, which is the overtone, gives rise to two bands at 1285.5 centimeter inverse and 1388.3 centimeter inverse, having intensity ratio of 1:0.9. Another example of Fermi resonance is given by aldehydes, in which carbon-hydrogen stretching absorption usually appears as a doublet at 2820 centimeter inverse and 2720 centimeter inverse due to interaction between carbon-hydrogen stretching, that is fundamental frequency, and overtone of carbon-hydrogen deformation bending. Fermi resonance is also shown by N-butyl vinyl ether. In this case, overtone at 810 centimeter inverse chances to coincide with fundamental band at 1640 centimeter inverse. The mixing of the two bands in accordance with Fermi resonance gives two bands of almost equal intensity at 1640 centimeter inverse and 1630 centimeter inverse. Fermi resonance is required to explain doublet in certain lactones and cycloketones. In large molecules, Fermi resonance is observed only when normal vibrations and overtones are in the same area of molecule, and also if symmetrical conditions are fulfilled. Now we'll study about the fingerprint region. This is also an important topic of IR spectroscopy. One of the important functions of IR spectroscopy is to determine the identity of two compounds. Two identical compounds have exactly the same spectra when run in the same medium under similar conditions. The region below 1500 centimeter inverse is rich in many absorptions, which are caused by stretching and bending vibrations. The said region is usually rich in absorption bands and shoulders. It is called fingerprint region. तो आपको ये फ्रीक्वेंसी की वेव नंबर की जो ये वैल्यू गिवन है ये आपको याद रखनी है कि फिंगरप्रिंट रीजन वो रीजन है जहाँ पे 1500 सेंटीमीटर इनवर्स के बिलो वाला रीजन फिंगरप्रिंट रीजन कहलाता है. हाउएवर fingerprint region of a given compound is unique. हर एक compound का एक अलग fingerprint region होता है. And compounds can be used to distinguish between compounds. Through this fingerprint regions, we can identify two compounds. Fingerprint region can be subdivided into three regions. First region is the 1500 to 1350 centimeter inverse. The appearance of doublet near 1380 centimeter inverse and 1365 centimeter inverse shows presence of a tertiary butyl group in compound. Gem dimethyl shows band near 1380 centimeter inverse. Out of two strong bands for nitro compound, one appears in fingerprint region near 1350 centimeter inverse. Second region is the 1350 to 1000 centimeter inverse. All classes of compounds such as alcohols, lactones, acid, ester and hydride show characteristic absorptions in this region due to CO stretching. Primary alcohols form two strong bands at 1350 and 1260 centimeter inverse and near 1050 centimeter inverse. Phenols show absorption at 1200 centimeter inverse. Esters show two strong bands at 1380 to 1050 centimeter inverse. Absorption in this region is 1150 to 1070 centimeter inverse. It is the most characteristic for ethers, that is CO stretching in COC group. Regions below 1000 centimeter inverse. The presence of mono-substitution and disubstitution at ortho, meta and para positions in benzene are detected by characteristic absorption in this region. A band in the region 750 to 700 centimeter inverse shows mono-substituted benzene. So in this video we have studied about the general introduction of IR spectroscopy, and then we have studied about the Fermi resonance and then the fingerprint region. These are important topics of IR spectroscopy. Thank you. To keep me motivated, like the video, share it with your friends and subscribe the channel.